Okay, so I think that we will start now. So again, hello everyone. So I'm Pierre Bonnel. I will be one of the speakers today. Again, I would like to thank the Green Forge Cup Association, the Casio University and AEYT for co-hosting and hosting this webinar. So I will be the first speaker today and will talk about the optimization and parameter sweep in Pyleecan. Then we will have Hélène Toubin for everything related to SciDataTool plotting and post-processing with Pyleecan. And Raphaël Pile will introduce everything relating to how we handle mesh with Pyleecan. And again, we have also other people within the chat that can answer your question if you have any. Okay. So this is a free part, the second part of the free webinars. So the first one was 2 weeks ago, and the recording is available on our website if you are interested. And the third webinar will be hosted in 1 week from now. It's entitled How to Contribute to Pyleecan, but even if you don't want to, you can still attend because it will help you understand how everything is organized and built within Pyleecan. And again, in Pyleecan, we are not looking only for code contribution, we are also looking for validation and so on for the global quality of the project. Now that everyone is away, I will remove my mask. It will be more easy to understand me. Okay, so as we said, so for today it will be a three-part webinar, multi-simulation, so parameter sweep and optimization, visualization, and mesh for Raphaël. Again, you can find the resources on our website. So his is pyleecan.org/tutorials. So you have all the procedure to install Anaconda and Jupyter Notebook. So you can interact with the code as we will present it to you. And at the very bottom here, you have the link to the previous webinar resources. And here you can find the resources for this one. So let's go back to the presentation. Okay, so before we start this webinar, I would like to do some short reminder about object-oriented programming, because that's the very key to understand Pyleecan. The idea is that in Pyleecan, everything is a concept black box that you can interact with in a normalized way. And the idea is that as long as you know which black box you need to use and how to interact with, you know how to use Pyleecan. It can look complicated, but at the end, it's much simpler once you know how everything is organized and what is the link between every single object. So the principle of an object is that it's, again, the point of a black box of a concept. So for instance, a slot. Here are two examples of slots that we have in Pyleecan. So this slot, we will define them with properties. The idea is that it's values that define what the slot is. For instance, on the second one on the right, we have H0 and H2 that define the height of the slot. So we have a global object that says that to define this kind of slot, you need to provide these two quantities. And in the code, you will create what is called an instance of this object with the very values that correspond to your machine. So the first thing is properties. What define my object? What are the global information to describe my object? And the second important concept is methods. What are the functions to interact with my object? The idea is that if we want to know the height of the slot, we don't want to go to take H0 and H2. We just want to ask the slot, what is your height? So we have a method which is known as comp_height that returns exactly that. And the idea is, again, here I've hidden both slots, so you don't have to know what is behind the curtain. You just need to know that you have the comp height method that exists and that will return the height of the slot. And then whatever the schematics of the slot, whatever the properties and whatever the values, it will always return what you are looking for. So you just need to know that in your object you have a slot object, and that in your model you just need to interact with the height of the slot. So then the idea is that, as I said, objects are about concepts. But we have lots and lots of classes within Pyleecan, so we need to have some kind of organization. So the idea is that we gather some objects in some kind of family, so that we have some very interesting link between each other. So for instance, as a concept, you have the lamination, the slot, and the machine. So the idea is that we first define the very top class, which is the parent of all the other classes. For instance, we have a machine class that will define all the other machines in Pyleecan. But this class is not a real one. It's just a fully abstract concept. So you won't create a machine object within Pyleecan. In fact, you will always create what is called the daughters of the machine class. The idea is that you have the machine class on the top, and then on the bottom, you have a machine doubly fed induction machines, for instance, which correspond to something more representative of what can be a real machine within Pyleecan. And the idea is that we say that the doubly fed induction machine is a particular case of machine. So doubly fed inherit from machine, and we can also say that doubly fed is a daughter of machine. So the idea is that we create what is kind of a tree or a family, so of some relation between all the classes. And why we do that is because every time we define something on the top of the tree, it benefits for all the daughter and every class at the bottom. For instance, if we define a plot method in the machine, every single other machine that we define as a daughter of machine will have the possibility to reuse this plot method. So you have to do the work only once, as long as you put it on the top of the tree. So that's very interesting. And something more is that, of course, the daughters are different for the top classes, you can also define some variants of the plot function, for instance. If you need to display something else for some very particular machine, you can redefine the plot, and you then can interact with it in the same way. So the idea is that, again, you have a black box, which is machine, which is a global family. You know that there are several kinds of machine, doubly fed induction machine, IPMSM, SPMSM, and so on. And the idea is that all these different daughters, as they are all the daughter of the same machine object, they have all the same property, they have all the same methods, and you interact with them the same way. That's why we define this kind of relation. So, on the last webinar, we mostly introduced the simulation object, which is the most significant one that you can interact with to run your simulation. But in fact, we have the simulation one is an abstract object, and simu1 is a daughter of the simulation abstract one. But the idea is that for now, we only have the simu1 object. So we have the habit of calling it simulation, but technically it's incorrect. The idea beyond that is if one day someone needs to define a simulation that is different, he can create a second daughter of simulation, and it will interact, and we can call it on the same way as we do for simu1. So that could be very interesting if we, for instance, start to work on some other simulation with some strong coupling, for instance. So the simu1 object is defined by its properties. So you have the machine, the input, and then you have the models, electric, magnetic, and forces for now. Then you have the var simu. So the idea of this property is to define how we will iterate on this simulation to run some others, for instance. In the first webinar, we have introduced the var load current classes, which is a var simulation that enables to run the simulation on several operating points. And the idea is that today we'll present you some other class that use these properties. And the last but not least, we have the post-proc list that enables you to define the post-processing that you want to run at the end of the simulation. I will come back to that later. And then the two most significant methods that you need to know for simulation is run, that will run everything, so including varsimu, and run single, that is more about running electrical, magnetic, and forces. So now the idea is that I will present you how we define a parameter sweep within Pyleecan. So the idea of parameter sweep is that we have a reference simulation that we want to find what is the effect, for instance, of the width of the magnet or the height of the slot on a particular output, for instance, the torque. So the first thing you need to do to define such a simulation is that we'll define a param explorer object. So param explorer, again, is an abstract class. So we will define the daughter param explorer set, which enables to define a variation of a parameter according to a set of value. So it's defined with a name. So for instance, a magnet width, a symbol, W4. The idea of this symbol is that it's something that's more convenient to call the parameters, and it will be used in the graph, we will see later, and the unit. Then you have the setter, so it's a function that will take a simulation, a value, and that will return an altered simulation. So basically, the simplest way of doing is just saying, okay, you take a simulation.machine.slot.h0 and you put the values and you have altered the machine and you return it directly. So it's just simplest thing you can do with a setter, for instance. And then the values. So what range of values should I put for this parameters? For instance, 11, 12, 13, and so on millimeters as the width for the magnet. So you define the input and what is the variation of your simulation through this param explorer object. Then the idea is that if we will run lots of simulation because we will variate lots of parameters, and if for each simulation we keep the flux, the torque, the forces, and so on, your memory can have some difficult time. So the idea is that we have introduced what is called the data keeper. The whole point of it is that we will extract what is meaningful to you. At the end, if you are looking to if you want to define a parameter sweep to find what is the best parameters for the torque, you don't want to know what was the value of the flux for every single simulations. So basically, for the data keeper, you will have again a name, so torque, symbol, TEM HV, for instance, unit, and then you have the keeper. So it's just a function that will take an output, extract something, do a post-processing or any computation that you want, and return a value. This value will then be stored in the result list at the bottom. And the idea is that we also have provided what is the error keeper. The idea is that if your simulation has an error for any reason, then we will call the error keeper and get the value. So the most simple one is just to return none, for instance. And then once you have all that, you have the var param object that will gather all this information to define your parameter sweep. So as you can see, there is a param explorer list that is a list of the param explorer that we have defined. So the list of the input that you want to change. Then a data keeper list, so the list of the output you want to keep. And then we have few options. So is keep all output is very interesting if you want to keep all output. As I said, the default behavior of multi-simulation in Pyleecan is that we remove all the output of every single simulation to avoid destroying the memory. So but sometimes you want to have that. So you have this option if you want. And then there is also the stop is error. So I've introduced the error keeper for the data keeper, but sometimes is one single simulation is wrong, everything is wrong, so you want to stop because something, there is something that you need to fix in your simulation. Okay, so you set all these properties again to define what is your parameter sweep, and you set this var param object within your simulation as a var simu property of simulation. Again, we'll see that in the notebook later on. So now about the workflow, what is going on when you click run on such kind of simulation? So first, we have the simu object with the var simu property set with the var param object that we've just defined. So we call run, that we call the run single and all the model of the reference simulation, and we'll have the reference output. Then we will generate the list of simulations that we need to run. The idea is that we will take every single parameter explorer and we will do the product. For instance, if you have a param explorer with 4 values and the second one with 5 values, you will define 20 simulations for all the combinations. So that's the first thing. So we define all the, so we copy the reference simulation and change every single parameters according to the param explorer. And then there is the is reuse. So it's a concept that we haven't pushed much further for now, but the idea is that you can extract some data from the output to enforce them within the simulation that you are creating. The idea is that, for instance, if you have a very long computation that doesn't need to be rerun in every single computation, in every single other simulation, you can directly enforce it without, which is more interesting. But for now, the only is reuse that we have is the possibility to reuse the FEM file that we draw for the machine. So you won't have to draw it for every single simulation. But for today, as we will present you only some parameter sweep on the geometry of the machine, it's not an option that we will be able to use. Otherwise, we will use exactly the same FEMM file, so they will be, all the simulation will have the exact same results, since we won't effectively change the parameters of the machine. So once you have the list of the simulation, you run every single one of them. And now you can create the X output, which is the result of your simulation. The idea is that X output is a daughter of output. So the idea is that, in fact, what we use the output of the reference simulation to initialize our X output. I will come back to that a bit later. And then we use the data keeper to extract from each output of each simulation exactly what we need. So now we have your X output object. So you can see that there is the properties from the normal output. So you can access to the reference simulation from electric, magnetic, post, and so on. And the idea is that if you go to xoutput.mag.tomAV, you will have the average torque of the reference simulation. If you want to have the average torque of every single simulation, then you will have to go to xoutput.dict that contain everything related to the data keepers, for instance. And you can also get the output list if keep all is activated. So now let's go to the notebook. So again, so this notebook is available on pyleecan.org/tutorials. And if you run this first cell, you will see if everything is installed properly. So I will, as for the first webinar, we will do now a small session of question and answer. So you have the time to download and install everything if it's not already the case. So for now, do you have any question about how the multi-simulation and the parameters the parameter sweep is working. Again, I will have a presentation just afterwards to show you in practice how it works. Okay, so okay, so no question for now. I will just carry on. For this presentation, I will be using a variation of the machine that we presented you during the last webinar. So I name it EPMSMB. Basically, just exactly the previous machine, but I've changed the hole on the rotor. The idea is that it's a different parametrization. That way I can have directly a parameter to change the angle of the poles. So I will start by defining the reference simulation, which is exactly the same that we have introduced in the first webinar. So first we define the machine. So we define it, I've defined it within the GUI, I've saved it in JSON, and then in one line I can load it, and then I can interact, plot it, and so on. Then I define my simulation. So the simu1 object, I give it the machine as a property. And I will define the magnetic model, which again is the mag-FEMM model, which is resolves the magnetic model by calling FEMM. Again, time and angular periodicity are activated, and all the other modules are deactivated. So we will run only magnetic computation. And then, so I have within my simulation my machine, I have my model. Now I need to have my input. So what is the current that I have? So the current is defined with the input current object. So I set my discretization. So I will have more than 100 time step, and the speed and the current that I have set here with I0 and phi0. A new option that we have introduced during the 2 weeks gap between the two webinars is that now you can set where the results of the software will be, of the simulation will be run. And for every simulation that use FEMM, where the FEMM files will be stored. So if I put that here, then all the FEMM file will be available in this folder. And something very interesting that we have introduced during the 2 week gap. During the first webinar, you asked about it. So now you can activate the parallelization of FEMM just with a single properties. So now here I define that I want to parallelize FEMM with 4 workers. I don't have to do any other extra work. So so now I have everything defined for my simulation, the input, the model, and the machine. So I can just call run. So you can see what the simulation is. So if I go to quickly, if I go to the folder that I've created, you can see that I have 4 instances of FEMM that are currently running, and that will solve quite quickly my simulation. Again, I have more than 100 time steps, but it's divided by 8 because we have the time periodicity, and then again divided by 4. So I will have my my result quite quite quickly, and it's already there. So something else also that we have changed during the 2 weeks gap is that we have completely rethought how we handle post-processing. So the command that we show you during the first webinar won't work anymore. So here is a new syntax, which is way more powerful. Hélène will talk to you more about it later on during this webinar. But you can see that we have the same result as before. And again, I have my torque as a function of time. So now let's dive in a bit more on the parameter explorer. So I have my reference simulation. I just run it to show you that the simulation was properly defined, but you don't have to. Everything will be handled through the run once you will have called the varsim. So here is two first parameter explorer set. Again, param explorer is an abstract class that you don't need to create. So I create two param explorer set. So the setter is just the link to the parameters that I want to change. So it's W4, the parameter of my hole. So it's the pole angle, the angle of the pose. So I have here a linspace to change the value of W4. Then I have also another linspace to change the magnet length. So it's W3. Obviously, for this presentation, we'll just have very few steps, but you can put as many parameters or as many param explorers as you want. But for now, I have only two values. So I will run 4 simulation as both parameters explorer set as two values. Then I define my data keeper. So here you have the first one is about getting the average torque. So I give what is called lambda. So it's a simple function for Python. The idea is that in Pyleecan, you have several ways of providing a function to the object. The first one works only for the parameter explorer set, is to provide the path. And then we change this with this line by something equivalent to that, basically. Then the second one is to provide directly a lambda. So it's basically a function in just one line. So it just say, okay, I take output and then I do that. So I return the average torque. So again, it's just a function in one line. And the third way of defining a function in Pyleecan is by providing directly the path to a Python file, and the function within the Python file need to have the same name as the file itself. So I will show you an example just a bit later. And the data keeper and the error keeper is the possibility just to take a simulation and I return null directly. Then I define a second one, just to show you that I can get as well the full radial flux. So I can have a list of matrix for the values of the slot. The command to actually get the radial flux is a bit complicated, but it's something that will be explained more in detail in the SciDataTool part. And again, if I have an error, I can just set a matrix of none. So now I have my reference simulation, so I can copy it. I just reduce a bit the number of time steps as I will run several simulations. It would be more convenient. And as I said, I just gather all the information that I just defined within the var param object. So the two param explorer set that I've defined, the two data keepers, and then I set some properties. Again, I deactivate the fact that I will reuse the FEM file as I'm changing some geometrical properties. Yes, so we'll just start running the simulation and while I'm explaining this cell. So now, I said that we have the post-proc list within the simulation. So the idea is that we can define post-function or post-method objects that basically have a run either property or method to be called at the end of the simulation. So the idea is that just by these very simple lines, I said that for the simulation that I've defined, I want to run all this post-processing, but I've defined only one, but I can define a very long list if I want. And this post-processing is just call this function within this file. So that means that at the end of every single simulation, I will call this file. Then there is also a postproc list at the end in the var_simu object. And this one has another meaning. It said that at the end of every single simulation that the var_simu will run, now run this post-processing. So at the end of all the simulation, I will run the other method. So if we go take a look at what I've defined, so basically, the first method is just plot the machine and save it. And the second one is just take all the images in one folder and generate a GIF from it. So if I then go to the folder, so to the result folder of my simulation, now I have the plot machine of every single step. I will show you better afterwards, and the GIF of the machine. The idea is that if you reuse this notebook, you will be able to generate really easily some very nice animation of your machine for your parameter sweep. So if I go back to the notebook, so all the simulation we are running, the idea is that, so I have the plot within, but every time you have a simulation that starts, you have a log that say where you are in the simulation, what simulation is starting to run, and then at the end you have the result. So you can check as long as the simulation is running if everything is right. Are you going to the correct parameters, and are everything going as expected? So now you have this kind of GIF that can be generated. So it's something that I've run before this webinar. I've taken much more values within the time step, so you have the detail just here. But all that was generated fully automatically with Pyleecan just by a clever combination of the objects. So I have the Parameter Explorer to change the parameter of the machine. So that's why you see some change in the angular of the holes and the magnet length. And on the top, you see that there is the number of the simulation and the corresponding torque. And again, at the end, we have two very simple post-processing. Just save an images and then do the GIF. So it's a very simple example of what you can do, but you can do everything you want. For instance, you can save all the data on some place. You can decide to run something else, for instance. You can play with the post-processing as much as you want. So that's quite a powerful option. So now I've run my simulation. So let's dive in what there is in the X output object. So you can see that when I call run, it returns me the X output. So first, you need to know that we define the X output to be handled as a dictionary. So you can ask what is the key, so what is the content of the X output with that. So you can see that we find back the two symbols that we have defined for our data keeper. So the first one is for the average torque, and the second one is the radial flux. Then I can access to the design variables for the parameter explorer list properties that I showed before. So here is a small loop to display what was the design variables. So I can get the name, so pole angle, the symbol, and then all the values. And as you can see, you have in order all the values that was used for the simulation. So I can see that for the simulation index 0, these was the two values of W4 and 3. Then you can go to X output and go to use it as a dictionary to get the result of any data keeper. So for instance, here is the torque for every single simulation that I have run. And now that you have that, you can interact with it as much as you want. Again, you have the power of Python for its scripting possibility, so you can do everything you want. For instance, I can ask at which, what is the argument, what is the index where the torque is maximum. So I get this ID. For instance, in this example, the torque is maximum for the third simulation. And then I can ask to the X output, get me the third simulation, because I have still the reference simulation within my X output, and I have the param explorer list. So I know what was the parameters for the third simulation. So I can just ask the X output, okay, take the reference simulation, apply again the param explorer, and then I have my simulation object, which is very powerful because now with that I can, so I have the best simu object. So now I can ask to plot what is the machine of the best simulation. But if I want, I can also call bestsimu.run. So if I do an optimization with 200 simulations, something very wide, then at the end I can say, okay, what was the best simulation with it? Okay, it's the 120. So get me simulation 120, run it, and now I have all the post-processing that I want for this very single simulation. So I can go even much further to understand why this simulation is better. Okay, so as I said, you can put within the param explorer and the data keeper some very complex simulation function. I've started with just change the value of one parameters, but you can do something way much interesting. For instance, if I use this script, so a file named scale slot with a function named scale slot that take a simulation as argument and values. And basically, it's a very simple script. I just multiply every single parameter of my slot by the scale factor. It's not that complicated to understand what it will do. So then if I define that, I will scale my slot between 0.8 and 1.5 times the normal size of the slot. And again, it's something that I can define very simply within Pyleecan. And I can combine it with other complex stuff without any problem. So then I can redefine again the simulation. I reuse exactly the same post-processing as before. I won't run it for this time, but as you can see, again, I can generate this kind of simulation and this kind of animation very easy. Again, before the webinar, I've run this simulation. And what is interesting is that the very last simulation of this animation is out of band. You can see that the slot will just reach the yoke. So the very last simulation of this simulation return an error. And if I go to check what was the result of this simulation, I do get none as expected because it's behavior that I've defined for my data keeper. So you can again run it and play with it to understand what we have done. And again, you can also create some very specific data keeper. For instance, you could say like, okay, I have my torque ripple. I will take the FFT of the torque ripple and then get the maximum of the maybe the amplitude of the third or fourth harmonics, for instance. And you can define that very simply, and it will be directly available for an optimization or a parameter sweep, which is again very convenient. You just have to define the script that will return this value, and then it will be handled as any other. I just realized that I forgot a graph on the first one. is that as we have as I show you during the first webinar, is that you can call plot multi on the X output and give it any combination of the param explorer and data keeper, and you will have this kind of graph. So you can see where all the simulation went. So in a very convenient way, I can have the graph average torque as a function of W4 with the unit as defined in the data keeper and the param explorer. Again, so you can have some very nice graph in a very convenient way. And we go even further in the next examples. So before diving into the optimization, do you have any question on the parameter sweep? For the post-process, so first question is, are post-processing function being evaluated after each simulation or after the whole parameter sweep? If I go back to the definition, the idea is that here I define the post-processing of my simulation. So there is a post-proc simu.postproc list. So this post-processing are called at the end of every single simulation. The idea is that when I run my parameter sweep, I will duplicate the simulation and remove the varsimu. So when I run the simulation, at the end of the simulation, I run the post-processing list. So this one is defined at the end of every single simulation. And then there is simu2.varsimu, which also have a post-processing list. And this one is only called at the very end of the parameter sweep. So you can do both, which is very convenient. And again, the idea is that on the first post-processing, I save the image of the plot machine. And at the end of all the simulation, I create my diff. So you can see what is the difference between the two functions, for instance. Second question is there some limits on the function that we can define in setter in Param Explorer set function? I don't think so. I think it will depend on your imagination. And if you find some, will be really interesting to discuss about it in the issue. Basically, you in the parameter explorer set, you have the whole simulation, so you can do everything you want. You can imagine that you will, for instance, you can even start to run something. You can start to, you have even access, for instance, to comp height or comp weight for the machine to change the parameter according to something. You can do some computation during the Param Explorer, for instance. So you do a very small computation, then change the machine according to it. You can do basically everything you want, as long as you use the content of the simulation object. And you can even, if you provide a script, you can have some import. So you can even use some external packages to have some inventive function or methods, for instance. So I expect that you can do everything you want, but for now we focused on some practical example, but normally you should be able to play with it. And you can do the same for data keeper again. You provide a function, and the function will be called at the end of your simulation to return a value. The value that you return will depend only on what you want and what you define. Okay, nothing else? I will continue on the optimization then. So the idea of optimization is that we will reuse some principle of the parameter sweep. Again, the very principle of object orienting is the possibility to reuse the same principle, and so you don't have to define the same thing twice. So we use this, so the simulation that we will run for the optimization is the same principle we have a reference simulation. The objective, we define it with data keeper. The particularity is that it's just data keeper that we will try to minimize. So it's always minimized. If you want to maximize something, you just need to minimize the inverse, for instance. And the result will be stored in an X output object. So all the post-processing that are available for an X output are already available for optimization. And someone that works for post-processing for optimization will benefit for anyone that run a parameter sweep or varload current simulation. So that's very powerful since we use the same object. And then the Pyleecan optimization is organized around two main objects. So we have opti problem. The idea is that there is an object that defines what is the problem to optimize in a more general way. So we have an object to define the design variable. I will come back to it a bit later. And we have another object to define the constraint. So you define everything in this object. And then we have another object that defines how to solve the problem. The idea behind that is that you can change both objects easily. For instance, if one day we want to introduce a new way of optimizing something in Pyleecan, we just need to define another opti-gen-alg, for instance, object. As long as it has the same methods, as long as we interact it with the same way, we can add new optimization algorithm with Pyleecan quite easily, and it will run on the same problem. You will be able to reuse all the complexity for the data keeper and so on, just by reusing the opti problem. So everything is split. So every improvement that we made either on opti project or on the solver will benefit for all the other solver and problem. For the workflow, it's a bit different for the var param. So we still have a reference simulation, but this time it's not run. So we just call the design variables to define a list of simulation. We run all of the simulation to have the corresponding output. And then according to the algorithm of optimization that you have defined, it will define then a new set of simulation that we run to have output and so on. And then at the end of every single output, we just call the data keeper and store everything within an X output object, so you can interact with it at the end of the simulation. So if I go back to the notebook, so we just take back the simulation. As you see, I come back to the first machine that we have defined on the first webinar, and I've changed again the number of time steps. So the objective of my problem are data keeper. So in this example, I want to maximize the average torque. So I can define again a symbol and a unit. So it will be reused directly within the plot. And lambda to say, okay, I have the output and I return minus the absolute value of the torque. So I will minimize that. And then I want to minimize as well the torque ripple. So it's a torque ripple peak to peak. So I just need to get to minimize the absolute value of this. So that's exactly the same data keeper as before. And then again, I can define as well the error keeper if I want. I just realized that again, I forgot something else for the complex, for the parameter sweep, is the ref simu index. Sorry for that. The idea is that these parameters enable to say the reference simulation is within the simulation that I'm defining. The idea is that I said that you need always to run the reference simulation before your the list of simulation. So if you want to run n simulation, sometimes you need to run n+1, which can be annoying. And in this particular case, I have a scaling factor of 1 on in my parameter set, which correspond exactly to the reference simulation. So I can say to Pyleecan, okay, the third simulation is the reference simulation. So start by running the third simulation and then generate all the simulation list and then run all the other one. Yeah, so sorry for this interruption. So let's go back to optimization. So objective are data keeper that we want to minimize. So here are defined two. Then we have the opti design var object. So there's few information here, but I will go straight to the code. So I will define two. The stator slot opening. Again, I can provide a more convenient name so I can know what I'm handling, and a symbol, a unit. And for this one, I will define an interval. So between 0 and the width of my slot. So I'm defining the range where we will try to find some values for my slot opening. And I can also give a get value function that enables to say how we get randomly the values for the first simulation. So here it's just an uniform distribution. And again, as for the param explorer, I have a setter. So I have defined what are the values. Now I define where should I put these values. But again, here I've put only W0, but I could have my scale slot method and it will work exactly the same way. And the second opti design var object that I define is how to change the magnet width. So it's a W4, here is a path, and here I define it as a set. So I provide 4 values, and I will only have values for these parameters within this for one. So you can define exactly what you are looking for. For instance, and again, here is that space is a list. So I think that you can, for instance, define a list of materials. For instance, if you want to have an optimization for what is the best material for my magnet, for instance, I think that you can have 4 different magnet material objects here. And I think it should work. I haven't tried, but I think it should be something very easy to define. We just provide the 4 values here, and here it's something like simu.machine.rotor.h0.max0.mat type or something like that. Then the constraint. So I have again a new object. So opti constraint. So I give a name, a type of constraint, a value for the constraint, and then again a function that will be evaluated at the end of every simulation. So here I've only a simple constraint is that I want to have my torque ripple lower than 75, but it's not very interesting for this optimization since we are trying to optimize to reduce the torque ripple. So usually when I run this simulation, the first simulation have some infeasible elements and then it carry on. And finally, the opti problem object. So as for var param, it's the object that gather everything. So simu, the simulation that we have, my list of design variables. So again, W0 within in an interval. Oh, sorry, I forgot I changed that. The width of my magnet within 4 values. Then the objective function that are data keeper to minimize, so torque and torque ripple. So maximize the torque, sorry. Then the constraints that are just defined here. And something interesting is that you can provide an eval function. The idea is that you can use the optimization of Pyleecan to optimize something that don't call Pyleecan simulation. There is an example in the test of Pyleecan. So if you want to benefit for the code that we have done for the post-processing and so on. So if you want to reuse everything related to the data keeper and so on, there is already a possibility. And there is an example on the test, but I won't go further. This is quite advanced. Okay, and then finally, I will run it now and explain it a bit later on. Okay, and then again, now you have the solver object. So here it's a generic algorithm. So if you click here, you have the explanation about what is the theory behind the optimization, how it works, and so on. But very basic is that, oops, sorry. In fact, I was already on the correct page. Yeah, so the idea here is that we define four we have a population size of 4. So each generation will have 4 simulation, and I've defined only 2 generations. So the simulation will be quite short. But if you look to the archive that we send you, you will see that there is the file that I will show a bit later that contains the result of a simulation way bigger than that. But again, you can parameterize your optimization with the object. I won't go further on that. It's more about optimization design. I will just present the object, not the theory. So when you call the simulation, you'll see that as for parameter sweep, you have the history of all the simulations that are run, which is quite interesting. So you can see that here I'm only again on the first simulation. I'm only on the first generation. It's a bit longer than I expected. You can see that for each line, you are where we are in the simulation, what are the design variables. So you can have a look during the execution about what was going on, if you are going in the correct place that you expect, if there is no very strange values. And you can again get the objectives that are printed so you can see what is going on. And something interesting is that at the end of every generation, you have a summary of what happens. So here we have a simulation that doesn't fit the constraints, and we can already see that it was the fourth one. Okay, so the simulation will carry on. Why it ends, I will just have a small talk about saving and loading in Pyleecan. In the first simulation, in the first example, we show you the save option. It's a method that you have on every single object in Pyleecan. So you can have simu.save, machine.save, and so on. So here I have simulation.save, and I provide the path to a folder with JSON. The idea is that we can save the object in two formats in Pyleecan, either JSON, which is something convenient to read, and H5, which is more about data. So once the simulation will be done, I will run that so you can see how it works. It should be over now. Great. So if I call that, and I come back to my folder, I have now my simulation, and I've saved it in the flat way, as we say. The idea is that if I go to RevSimu, I have all the parameters of my simulation, which is very convenient because I can, when I run something, I know exactly what I've run, what were all the parameters within it. And if I want, I can change it. Design are very understandable files, so you should understand what is going on. And the idea with the flat save mode is that when I go to machine, I have only the definition, I have a path to the machine file, which is in the same folder. So if I go to machine, to the corresponding file, I can then see what was the parameter of the machine, and then same for the materials. So the idea is that it's more convenient to read that way. And then in my folder, I also have saved the result of the optimization. But I will come back to it. So H5 is a very specific format. It's quite optimized, but you will need to use either Pyleecan to read it or a specific software. But that's still something very interesting to use. So here, rather than showing you the possibility on the simulation that I just run, I've run before this webinar the same simulation, but on with a population size of 20 and 10 generation, so 200 simulation that I managed to run within only 1 hour. And now I can just so I can have the output.save, so it's something that I've done before, and now I can just have load and the output, and I get it back. And if you take a look at the size of the file within the archive, you will see that it's really, really short for what we have simulated. Again, 200 simulation, but as we use data keeper at the end, we only have the few array of /200, but all the power of the optimization that I've run are available within the output in a very short file, which is quite convenient. And again, then I can see what is in, I can reuse exactly the same line as I have during the first, during the parameter sweep. So I can see what is inside my X output. So we have my 2 data keepers and 2 others that was automatically added. So I can see the number of generation of each simulation. The idea is that when we run an optimization, at the end, we completely forgot what was the behavior of the simulation. It's we handle it as if we have all the 200 simulation at the very beginning. So it's more convenient and we can reuse everything. And then I have isValid, so I can see where were the simulation that failed the constraint. I can get the design variables, and you can see that they are stored in the param explorer list from X output. The idea is that we have the opti design var object that defines the interval where we can find our W0 value, for instance. But then Pyleecan will create param explorer object. So you can reuse everything that I showed you during the parameter sweep example. And so as you can see, I get all the parameters. So I can get on this as the same way what was the value of W4 for all of my simulations. Then what was the average torque for all simulation? And again, if I want, I can get the index where the torque was minimum, so maximum, and the ID of it. And again, I can ask regenerate me the simulation of this particular index. So then I can run it and further investigate why this simulation was better. So, and all these data are in the very short file, and you have all the power of the optimization without having to keep all the data that you don't need. And again, you can get them easily afterwards. And last but not least, here is an example of some plots that you find on the X output. So you can see again what where the generation goes. So you can see what was the value of W0 and W4 was investigated, what was the output space, and so on. And in the Pareto front, you can also plot that. you can have the possibility to have a small tooltip that explain you what individual that is. So in fact, now I can just say, okay, get simulation 21, and I will be able to run this point if I want. Okay. So that's the end for me for the optimization. If you have some question before I'll let Hélène continue with SciDataTool object. How can you overwrite the evaluation function? For example, if you want to run several loads before being able to get all the results for the function. I think what we can do, it's nothing that is not available yet, but it's something that we already thought. The idea is that we want to be able to do multi-simulation of multi-simulation. Again, the idea is that when you run a multi-simulation, you duplicate the simulation, put all the multi-simulation parameters at none. So we can have two multi-simulation parameters. So the first one will duplicate and put the first parameter at none, run all the simulation. All the simulation have the second multi-simulation parameter, which is not none. So it will run lots of simulation. And then you will have the data keeper of this one that will return some values. So it will return for all the other simulation. And then you can, on the first multi-simulation, have a data keeper that will get all the different points. I'm not sure if it was really the answer you were looking for, but it's something we have not yet in the software, but it's something that we can work very easily for that. Is there any way to save the population of each generation while the optimization is running? Of course, again, we duplicate the simulation, so the post-proc list option is still available. So you can, if you set a function in your post-proc, you can save it and you will get it. Okay. Any other question, maybe? Okay, so I will let Hélène continue. If you need any assistance on the optimization, or if you have any feature request on this, don't hesitate to go on the GitHub so you can, so we can interact and change about what we can do next. Thank you for your attention.
Okay, so hi everyone, I'm Hélène. So I'm going to introduce you a project that we have started for data visualization. So this project is named SciDataTool. So the idea of this project was to help us handle scientific data, and especially Fourier transforms. We do a lot of them, and we wanted an object in which we have all these methods in one single place, and so we don't have to worry about it all the time. Sorry. Okay. So the idea is that we have a lot of physical quantities, which may seem very different, but at the same time, it's only signals. So it could be multidimensional, so it could be 1D or 2D, 3D, and ND, etc. It can be defined in the real domain, so in time and space, but also it could be defined in the frequency domain. So for example, we can have the current, the Fourier transform of the current versus frequency. We can have a 2D FFT or 3D anything. We can also even have a short time Fourier transforms for the noise, for example, but we want one single object or one single tool to handle all this data. We also want to reduce the storage space so that it takes the least memory possible. So to do that, we needed a generic object. and methods to go from one representation to another and to reconstruct a field that we had reduced, for example. So that's why we started the SciDataTool package. So it means scientific data tool. So it's been developed by Greenforge Corp. It's still ongoing work, but you can contribute to it too. It's also an open source package. You can find it on GitHub as well. So for now, it includes slices, Fourier transforms, periodicities, conversions, and interpolations. So in one single object, you can do all this manipulation on data, and it's very helpful to do some nice plots, as I will show you later. Just to explain the idea of SciDataTool, it has 5 main objects. So first we have the axes. So those are 1D objects, for example, time, we have angle, we could have the radius, the z direction, etc. So there are 2 objects to store that. So we have data 1D, which is simply a storage of this vector. And we also have data linspace, which allows to store it as just the initial value, the last value, the number of elements, and that's it. So that's 3 floats instead of a whole vector. And it also has metadata. So for example, you can set a name, a unit, a symbol, and then when you extract the data, you can get this metadata as well to do some very nice plots with automatic labels and so on. So we have these axes. Then we have a field. So for example, we could have torque or current or magnetic flux. So those fields, we are going to put them into data time or data frec. So data time is for a field stored in the real space, so in time, in angle, for example, whereas data frec is for Fourier transforms. So this field, it has a first attribute, which is a list of axes. Because when you have a data, you need to know on which axis it was created. So it's very important to keep the axis with the field itself. And then we defined a 5th object, which is vector fields. So it's used for vector fields. For example, the magnetic flux, you can have the radial component, the tangential, and the axial, for example. So the idea was to gather those 2 or 3 components into one single object. So it's basically just a dictionary of components, so a dictionary of data time objects, for example. Then to get the data that you have stored in those objects. So the way to create them, I will not introduce it today because it's a bit complicated, but you can find it in Pyleecan or on there is also a tutorial on the GitHub of SciDataTool. But the more interesting part is how to extract the data once you have created it. So it's the get-along methods. So it's a whole family of methods. You have get-along, get-magnitude-along, etc. And the idea was to try to develop a user-friendly syntax, so to extract what you want exactly. So here are a few examples. So for example, if you define an axis as being periodic, for example, time, you say, okay, my time is periodic. It has a period of 8. So I will only store 1/8 of my signal. And then if I want to reconstruct the whole vector, I would just call time. But maybe for my computation, I will need only 1 period. So I can call, as you can see here, 1 period or anti-period if it's anti-periodic, or the smallest period there is. You can also extract indices from your axis or along your axis. So if you call, let's say I want the torque at time for the first index, so this syntax, it will extract a slice of your torque at this index. You can set a list of indices or even a range of indices. You can also want to slice along a given value. So I want the time of, I want to slice at time equal 5 seconds, for example. You can also do intervals. It also understands mathematical expressions. So for example, here pi/2, it will know what it means. And you can also specify a lower or upper bound. So for example, angle below pi. It can also do sum along the axis, as you can see here. And it can also convert into other units. So the one that is mostly used in Pyleecan is the conversion from radians to degrees, because we decided in Pyleecan to store everything in SI. But for the plots, it's better to put it back in degrees, for example. But it can also understand any, well, maybe not any. Maybe you can find some conversions that don't work yet, but you can contribute to extend the conversion dictionary for that. We can also do normalization. So for example, if you do an FFT and you want your FFT axis not to be frequencies, but electrical orders, you can use this syntax. You can normalize also a field if you have a normalization value. So for the Fourier transforms, you just need to replace time by Frec and the angle by wave number. So for the time being, there are only those two matches between time, Frec, and angle wave number, but it can be easily extended. So yeah. And finally, you can do interpolations. So if you want time over a different vector, you can use this syntax, axis data, and then you specify what is this axis data. So it's an array that you can define. So let's see what it looks like in the notebook. Okay, so. Okay. So the beginning of the notebook is the same as before. So I first started a Pyleecan simulation to have data along angle and time. The idea was to be able to show you nice plots. But the simulation was already launched, but it doesn't take too long because it uses periodicities, as you can see here, and also parallelization. So it's quite fast. So we did two simulations, one with an input current here, and the second one in open circuit, so without current, so we can compare both simulations and see how we can easily superimpose graphs using the plot commands. So the first thing to do is to see what we get after the simulation. So it's all stored in the output object, as you have seen before. So for example, the torque will be stored into a SciDataTool object. So it's going to be a data time object here. And if you want to see what's inside, we use the getAlong method. So if I run it, here is what I get. So I get a dictionary which contains the axes. So here I have only one, it's time. So I have a big array for the time. Then I have the torque here. So big array again. And at the end, there are other keys in the dictionary. So it's actually metadata regarding the other axes that could be present in the object. And it's used in the plot commands to do nice titles and others, but it's not very important. So as you can see here, we have an array of size 50 times 8. So that's 400. But if we want to reduce this, I mean, if you want to do computation using torque, but you do not need the whole signal because you know it's periodic, you can use this syntax, spawnless period, and you will get only the 50 values of your time vector here and of your torque. Okay, so that was just to show you how to extract data. But then we want to show you how to plot it. The idea is that the syntax is exactly the same between extractions and plots. So that's why I wanted to show you how to do both. But in plot methods, everything is already implemented. So it's rather nice. So the idea is that we have created generic plot commands. So we have 3 plot functions, sorry. We have plot 2D, plot 3D, and plot 4D, which just takes data, so arrays or lists. We input the labels, the titles, etc. And it just allows us to unify the way the plots are formatted so that they always look nice. You can set, in the config dict, you can have the font size, etc. Everything. And then the more interesting part that I want to talk to you about today are those two methods, plot 2D data and plot 3D data, which can only be called on SciDataTool objects because they will need all the metadata, so the symbols, the periodicity, everything, to create all the titles, the labels, and so on. So for example, here we are going to plot the torque along time. So we use the same syntax. And we get a plot with automatically the good label. So we have the torque here, the time, and a nice title. Then if you want to see the same smallest period command, we can do it. And we can see that the plot is automatically reduced to 1 period. I told you about vector fields objects. So objects for vector fields. So for example, the magnetic flux density is a vector field object because it can have several components. So if we use this command on B, we get two plots, one for the radial flux density and a second one for the tangential flux density. If we had three, we would have 3 plots. If you only want one of them or two, you can specify it using the component list as we can see here. So here I only have one for the radial flux density. Here you can notice that B has 2 axes actually. It depends on time and angle. So in this plot, I only said I wanted B as a function of time. But what about the angle? So the idea is if you don't specify anything for the other axis, it will automatically slice at the first value of this axis. So that's why here in the title, it says for angle equals 0 radian. But of course, you can ask other values. So that's what we will see now, how to slice your data. So let's say I want the same plot, but at another angle. So for example, pi/6. So if I run this command, I will get a plot at this specific angle, and it will be written in the title here. We can also even superimpose several slices. So here, for example, I'm asking for the angle at index 0, 10, and 20. So I get 3 curves superimposed. And we have, so here are the indices, and in the title, we get the corresponding values, which can be nice. And in the legend as well. So we still have a little work to do on the formatting because there are many figures after the comma, but anyway. So that was for real slices. Now, the most important feature that we wanted in Pyleecan was to easily compute Fourier transforms because I think we all have this experience of trying to implement it and we forget to multiply by 2 or something like that to do the FFT shift and so on. And so it's quite annoying. So to show you how interesting it is to use SciDataTool, in this example, I will do the FFT manually as you would do in your script, and then I will show you how to do it with SciDataTool. So let's try to do the FFT of the torque in function of time. So we get the torque values. So to do that, I take my object and I just take the values field. Then I take my time, the initial, final, the number. I reconstruct my time vector because it's a lean space, so I didn't have it before. Also, my torque was, well, it was periodic, so I need to repeat this torque 8 times because I had an 8 periods. Okay, I do that. Then to do the FFT, I use the FFT package from NumPy. But then I need to divide the first value by 2. Then I need to do the FFT shift, multiply by 2, divide by the number of time steps, etc., etc. Then I take the absolute value to get the magnitude. Then I need to compute the frequency. So it's okay, I will not describe all that. And then finally, I do the plot. So here is the result, the resulting plot. Okay, that was, I think, a bit annoying. And also you could have made many mistakes in those few lines if you forget a shift or a division by 2 or something like that. So SciDataTool has all these methods implemented in it. It's hidden, so you don't have to worry about it. So you have only one line, actually. It's only just gate magnitude long frec. You can specify an interval. And you can do the same with the plots. So let's run this. So we see that we get the same plot, the exact same one. Another interesting thing is that since my talk is periodic, I get a sparse array for the frequencies. So that means that what it does in SciDataTool, it only computes the FFT over the small period. And then to get the right frequencies, it just multiplies it by the good factor so that we get the right frequencies. So we get a sparse signal, so it's much nicer for the computation cost and so on. We can also do the same along wave number, so along the angle. And also in Pyleecan, you can automatically detect the fundamental, which is computed from the machine data. And so it will plot it in black as in this plot. Then you can also easily convert or normalize data. So as I showed you this syntax before, so here, for example, I want the same FFT, but in electrical order. So I just use this syntax and I get my FFT axis as electrical orders. Then I can also change unit for my field. So here is the stator flux linkage. So it has 3 phases. So you can see that if you ask it along time and phase, it understands that since it's a list of phase, it needs to superimpose the 3 curves. It's automatical. And then if I want to plot it to change the unit, so here we were in Weber, and now it's in Maxwell's. So you can see the change of unit here. We can also change the unit for axis. So for example, here is B along the angle in radians, but it's much nicer to put it, oops, sorry. To put it in degrees. And we can also change it to distance using, again, data of the machine. Then we can also compare several fields. So we remember we had launched 2 simulations at the beginning, one with currents and the other in open circuit. So we can compare both in the same graph, simply using this data list. So you can superimpose as many curves as you want, and you can specify the legend so that it appears nicely in the graph. We can also compare FFTs. So it gives this kind of graphs. And finally, there are some nice 3D plots. So here we are going to work with the flux density, which is 2D. So we can do a surface plot depending on time and angle. Here it's a little long because it's the matplotlib plot surface, which is not very fast. In the meantime, I will launch the other one. So here again, it's always the same syntax. You specify the axis you want in your plot. You can do slices, you can change the units. It's always the same principle. So we get this nice surface plot. If you want to see it from above, you can use is2D view, like here. You can do some 2D, no, that's a zoom in for the smallest period. So we have specified smallest period for time and angle here. We can also do some 2D FFT. So here I also use the normalizations for the FFT axis. So electrical order and spatial order, we can see here. It can also be viewed in 2D. Okay, so that's the nice 2D FFT plots. And just to show you, we haven't shown it before, but we can also compute forces in Pyleecan using a Maxwell tensor. So here is a plot of the force that was computed during the simulation using Pyleecan. Okay, so there are many other things about SciDataTool that I didn't talk about. You can find more about that on GitHub. You can open issues and so on. There are also other tutorials more detailed about SciDataTool. But if you have any questions, just you can ask them now. Yes, just something I didn't say. Here, where I superimposed the two curves, the idea was to be able to compare several simulations. And also, you could also superimpose fields that do not have the same discretization. So it's very powerful, actually. I don't know if there are any questions. I can't see them. No. Okay. So thank you. I'm gonna let my colleague Raphael finish for today.
Hi again. I'm going to switch. Back here. Okay. Okay, so I'm going to make a little focus on how we handle mesh and solution objects in Pyleecan. As some of you may know, it's a tough question because there is probably not a perfect solution for everyone. So we definitely make a focus on what were our needs, especially handling different fields of physics together. But it's still under construction, and if you have better idea to propose, better software to use, we are very open to any proposition, and you can discuss this topic on GitHub. Opening issue doesn't mean you have to code to be a developer. There are very powerful and important contribution just by talking on the subject, talking about your experience on the subject. So feedbacks are very welcome. To start with the more general object we have developed right now, we have defined a class mesh solution. So as its name implies, it's made to contain both mesh and solution together. So we can make any plots by knowing both and make the link and have methods that work on both at the same time. So of course it contains mesh and solution. For the moment, we have chosen to contain list of mesh and list of solution, but we mostly use at the moment one mesh and several solution in the same mesh solution. So for example, FEMM, you will have the same mesh at every time step, but you will have the new solution of every time step, which is saved inside the solution. To be more specific on solution objects, today the solution object can be defined with three different type of classes: solution maths, solution data, and solution vector. Solution data and solution vector are related to SciDataTool. In fact, it's just a way to store SciDataTool object, as that Hélène just talked about. So I'm not going to go any more detail about this, but I will show you some example later with a solution mat. The idea of solution mat is just to store the solution as a matrix. That's what the name is, mat, inside it. and to reuse it later for, it's mainly dedicated to application, matricial application. So like dot project using NumPy. That's very handy. Then the mesh contains, of course, the nodes of the mesh, so the coordinates, and the cells, meaning the connectivity. So for the moment, we have all defined point-mounted cell mat objects, which work the same way as solution mat. So you only store some matrix. But if you have better idea to propose, you can define more general node and cell object, or even more general mesh mat object. Finally, if you are more into finite element analysis and you want to have the hand on the finite element interpolation, we are working on some interpolation objects. So in this interpolation object, we are putting all the useful and classical methods like computing shape functions, the Jacobian matrix, and all the methods used to perform interpolation, so scalar product and quadrature points such as Gauss points. So there is a lot of work to do on this part, so any contribution is welcome as well. So this was to give you an overview of the mesh solution architecture, and now I'm going to show you more some application using FEMM and so on. Up. Get back to up. I guess yes. Okay. Up. So I have reused the FEMM simulation of the previous webinar. So if you want to rerun everything, it will take just like 1 or 2 minutes just to rerun the 16 time step. But everything is like the last webinar. And I'm going to use this electromagnetic solution to show you what the mesh solution model is capable of. So the basic idea is to simplify our lives when we want to do plots and operation on the finite element solution. So the only important parameter which has changed prior to the last webinar is this parameter. So in the magnetic MagFMM object, you have to activate this option to save the electromagnetic mesh and solution from FEMM. And now, so let's say everything is run. If I want to plot the mesh, I can do it like this. I need to run the simulation. Okay, sorry, the simulation is not run. So up, up. So it's going to run a few time steps. So I'm going to first say what each line is doing while the simulation is running, and then I will show you the result. So the first line is a method from the mesh solution. So inside the output magnetics, there is a mesh solution that is stored to store the flux and field, magnetic flux and field inside there. And of course, the mesh. So first method of the mesh solution is plot mesh, just to display the mesh. You can perform some operation because inside FEMM we define some groups which are subpart of the electrical machine. So for example, the stator. And you can also plot the group together, so several parts together, for example, the air gap and the stator winding at the same time. And you can also perform intersection of subpart of the mesh. So the two last lines are the intersection of the stator between the stator and the group composed of both air gap and stator winding. And there I've just switched the air gap from the other side. So it's the intersection between stator plus air gap and the stator winding. Then I'm going to plot the different solution, and you still have the group. So up the solution, up should be okay. Let's give it a try. Okay. So here you have a little warning because in order to perform the different plots and the different display, today we are calling a third-party library, which is called Pyvista. It's a very handy library to perform all the plots which rely on mesh because it's really fast and effective. So here, yeah, so we got the FEMM, the mesh from FEMM, just the mesh was extracted from FEMM. So here we see all the subparts. And as you see, that's why there was warning. It's defined in 3D. So, but in fact, the mesh is in 2D. So this is just the reason of the warning we have seen. So now I said I'm able to extract the stator mesh. Here you go. You can see just the stator mesh alone. Up. Then I want, in fact, to get both just the stator winding mesh and the air gap. So here you see, this is the sliding band, just so of course there is no mesh on the sliding band. Up. And then here comes the intersection between groups. So it can be up. So here you see the intersection between the stator mesh, the windings, and the air gap. And now if I do the same but with the windings, up, of course, I will get only the line of the windings. So these lines are defined by two nodes lines. So it's decomposed into tiny segments all along this. What is displayed is just to some segments. And now we would like to see the electromagnetic solution. So here you go. You have the magnetic flux density everywhere in the machine on each element. You can display that. And as I said, you can extract only subpart of the machine and see same way the FEA solution. So that could be very interesting to, for example, compute the losses or for example, losses on only some part of the machine, such as the stator or the rotor. You could, yeah, or thermal solution. Up, and the last method we got today is a glyph. So the plot glyph method allows you to plot a field as arrows. It's equivalent to the quiver method from Matplotlib or MATLAB. So it's exactly the same. So here you see the magnetic flux density flowing into the machine. So for example, for the magnetic flux density, it's much more adapted than just a plot contour as before. So here for the different plotting method of the mesh solution object. Now I'm going to show you some concrete application where I extract and post-process some data from the electromagnetic solution. So first, how to get the magnetic flux density is quite easy. You got a method dedicated to this, which is called getField. And you will see, so here I've got my 64 time step, my 9034 elements, because the magnetic flux is defined per element, per triangle of the electromagnetic mesh, and the two components. What's hidden inside this are the different SciDataTool objects that are being used to store the solution. But you find back the same structure as Ellen talked about before. Then what another powerful tool is to extract a subpart of the electromagnetic solution. So what I do is I get the group of the stator with this command, and then I can extract the magnetic flux density and the magnetic field from this subgroup. And yeah, you will see, okay, my magnetic flux density has the same time step, the same number of components, but definitely the number of elements has reduced because I only got the elements related to the stator. Then you could perform some operation depending on what problem, physical problem you want to solve. For example, there I want to compute the electromagnetic energy density on every element, and I want to display this result with the previous plots. So absolutely no problem. Since I've extracted some matrix just before, I can use NumPy to perform to compute the electromagnetic density for energy density. Then I need to define a solution math object. So that's the part here. So it's a bit, of course, it's a bit like a solution data. All the SciDataTool objects, you need to define some axis. So here I got the time in this component. Since it's exactly the same as for the magnetic flux density, I just copy the time, the shape of the electromagnetic solution. And then I define my solution math object. So I'm going to give it a label for all the plots. I'm going to indicate the type of cell that are used in this solution to make the match with the match. Then I put the field I have just computed and the axis. And this is enough to perform to get the solution inside the mesh solution of the group stator and to get the plot I want. So if I execute this, yeah, there you go. I have just computed the electromagnetic energy density in every element of the stator mesh, just in a few lines. And of course, you could do a further analysis with any of it. I can also perform some operation on the mesh. So I can extract, for example, the nodes of the mesh. And let's say I want to perform a rotation of the mesh of an angle of P. Then I'm going to just extract the mesh, perform the rotation with NumPy library. So it's just a matricial operation. And I put back the new coordinates in my mesh solution object. And then you will see, then yeah, my mesh has rotated of an angle pi indeed. And what's cool is that the previous plot with the operation I've done is still working. So as you see, I've still got my electromagnetic energy density correctly computing all elements, but I've taken into account the rotation. So I let you imagine all the different possibilities that you can do. The final part is the more advanced. Is really if you really want to define yourself the mesh, the different part of the mesh. So the different possible mesh objects are there are two possibilities. There are mesh maps. So as I said, you store everything in a matricial and NumPy array to be precise, to define quantity and north coordinates. And the second object is mesh VTK, which is dedicated to visualization to make all the plots before. Of course, in Pyleecan, we keep switching between these two objects. If today, if I want to make some operation like I just did before, I will use a mesh map. But once I want to make plots, there are methods to perform the conversion between the two objects and get the plot from PyVista. So here I give you an example of a mesh map object that I defined by hand. Of course, you don't have to do that yourself when using FEMM. Everything is automated, but this will be useful if you want to make, for example, a coupling between Pyleecan and another finding element software. So interesting to have that. So here you got some methods to add different points of the mesh. And then I'm defining the connectivity of the triangle. So it's a cell mat with 3 nodes per cell. And then I give it a label, triangle, to indicate that it's indeed a triangle. And I put it in the mesh solution. I put it in the mesh solution so I can visualize it with the method from before. So, perfect. I got my 3 different triangles that I've defined just before here. Okay. And then I can define another solution math object. So as before, I want to have, so here, there are 5 points, and I want to define solution math as point. So the main difference comparing to before to the electromagnetic solution here is my type of cell can be point if I want to define value point-wise. And then I've got only one try step, and I define the field as with this random value. And exactly the same way as a mesh, I can perform plot. So yeah, I can see my field plotted here as I defined it. So everything is working. Okay, and of course I can also define vectors. There I define a new axis, which is components, and I can, if I've got components, I can use the plot leaf quiver methods to see my field, and there you go. You can see arrow as defined everywhere on the field. So this is strictly equivalent. You could do that with SciDataTool object as well, because you might want to extract the FFT of your field at any frequency, and then you could do exactly the same plots with the same methods. Okay, and the final step is here I have take an example where I generate a GMSH mesh with Pyleecan. So this was already showed by Pierre before. But what I'm going to do here is I want to save this mesh externally in an external file, a point mesh file. And then I want to show you how you can import an external mesh using Meshio and PyVista. So here I'm going to execute this. So now I have locally a mesh which is saved, generated, and saved on my hard drive. And if I give the path to this mesh on my drive, and okay, so this is the mesh that I've just generated. And if I want to read it, we use, right now at the moment in Pyleecan, we use Meshio because Meshio is able to do the conversion between a lot of different type of mesh file. So it's very powerful to change from mesh to VTK, for example, in my application. So here I will do that. And now I have a point VTK object, which is the type of file which can be read by PyVista. So I can easily define a mesh VTK object, so which is using PyVista, to load this file and to read it. And that's the final step. So, oh, here you go. So now I have a mesh object which is defined with my 3D mesh that I have imported from a third-party software. And I could do all the operation I want to do, like the one I showed you before with the energy density computation. So, okay, I think it's already a lot to see for today, and I'm going to stop here. But as I say, it's still under construction, and any feedback and contribution are welcome. So thank you for your attention. Yeah, and of course, if you have any question, I can answer it now. If I can see the... Je les vois pas? Okay. Okay. So if there are not any questions, I'm going to let Pierre make the conclusion of this webinar.
So thank you, Raphael. Okay, so this whole webinar was all about showing you how you can play with Pyleecan, how you can create some very strange and very advanced and interesting simulation We take a lot of time to build these notebooks, so you can experiment with that. You have everything for adapt and create your own parameter sweep. To go further with SciDataTool, you can try your own syntax and see what will be the result. You can define your own simulation and retry the same post-processing that we have done, and same for the mesh. So everything is here for you to experiment with. And as Raphael said, we are very open for any feedback and contribution on Pyleecan. Again, just saying, what do you think about this model? Did you see this publication? Is something very precious for Pyleecan, because it will fuel the next model for Pyleecan. Even if you don't have time to contribute yourself, that's still very important for us. And even if you just have some experimental data, so that we can challenge our model. So next webinar will be in next week. So it will be all about how to contribute to Pyleecan. But as I said, in fact, it will be, we can say it's advanced, because we will go more in depth about what is the very architecture of Pyleecan. So we'll understand how everything is organized. And so even if you don't have the time to contribute to Pyleecan, it will really help you to understand what is really going on and why it's as flexible as it is. So that's still something very interesting for everyone. And the idea is that we will also take the time to introduce you about how GitHub works, and some global advice about how to code in Python as well. So that's still interesting for that again. So we will, once this webinar is concluded, we will upload the video as well. You can again continue to follow us on GitHub, so you can see what are the current developments. We have quite a lot of discussion currently about the coupling with Elmer, for instance. So everything is quite moving a lot currently in Pyleecan. So maybe you saw that there was a release between the two webinars, and I think that there will be a new one for the next one. So if you have any feedback or feature, maybe we can take the time to include it for the next webinar. So that would be very interesting. Okay, so I just see if there is no last minute question. Okay, so thank you again, everyone, and see you next week.